Hey guys, even though it was part of summer assignment, I thought I should spend a couple minutes just to make sure you kind of understood a few things that I don't really want to spend much class time on, okay? Specifically in the area of measurements and calculations, okay? So to start with, obviously metric system you're expected to know about, okay? So you should know your base units. Mass is measured in grams, volume is measured in liters, length or distance is measured in meters. We'll mention the word coulombs along the way, but don't even worry about that one. Time is measured in typical time units, but we use seconds for the most part, okay? And of course, there'll be the metric prefixes that you're supposed to be familiar with. So in chemistry, I will say honestly, most of our work is kilo, centi, milli, okay? So beyond a doubt, those got to come to you automatically, okay? Now, one of the units we're going to do, nano, will come up a bit, so I'm warning you, you will definitely use nano a bit, but that's not, it's really just that one unit. Otherwise, yes, you'll see some of the other ones in homework questions or whatever else, but generally not so much on tests, okay? But doesn't mean I'm letting you off the hook with it. What's on this slide, you really should be able to handle, okay? If you are honor students, it should be in your wheelhouse, okay? In the metric system, there are a couple other things that you should know. Specifically, really, this one is the one that comes up the most, but metric system was chosen to really make sense, okay? And so they wanted the different units to match up in some way. So liters does relate to meters in a way, or more specifically, a liter is defined as a cubic decimeter. And a milliliter then means it's a cubic centimeter, okay? And this one would be true too, but we don't talk about kiloliters. And in physics, you might talk about cubic meters a bit, but not here, okay? But this middle one, okay, yeah, very, very important. Okay, so keep that in mind. The SI system is really part of it. Okay, it's Système International, because the French put things backwards. What can I say? So it is part of the metric system, but in the SI, instead of telling you can measure in grams and you can measure in centigrams, you can measure in kilograms, what they want to do is make sure that everyone was recording things the same way to be shared internationally. So mass is always recorded in kilograms, length is always recorded in meters, volume is always recorded in cubic meters. They figured if we're using meters for length, we might as well use cubic meters for volume. Time is seconds, etc. So there's a subset of metrics that are very specific SI units, okay? Now I'm mentioning that because I'm required to. We're not going to worry as much about that in this course, okay? So, this is just one of those, okay, got to mention type of things now, we move on, okay? Significant figures and precision. Okay, so one of the things that bothers students a lot is that in math, you might do some calculation and you get, 2.89543 and you're just going to say, all right, it's about 3 or it's 2.9, whatever. In science, we go by measurements, not just numbers, okay? We're not counting things per se, we're measuring things. And a measurement is only just so good because it depends on A, how thorough you are, but B, how good the device is. For example, look at these two rulers. Both of them are measuring the same thing, but notice that this one has a lot more divisions on it than this does. So on this one, I know it's between 2 and 3, so I could estimate that it's 2.5. Whereas here, because of the extra lines, I see it's between 2.5 and 2.6, so I could estimate it's 2.55. This is showing more precision. It has an extra digit to it that is reasonable, not just something that we throw on there, like throwing on a 0 here. You could throw on that 0, but it has no meaning because there's no way you could say 2.50 based on the device that you're measuring with. This device is only good to 1 decimal place. This device is good to 2 decimal places. So we have to keep track of significant figures to show how good a measurement is in terms of its precision, its thoroughness, its consistency. Okay, so we have to talk about these sig figs all the time, okay? So when we're talking about sig figs, Okay, it's based off of measurements, and a measurement, again, is only just so good. So when we look at a number or a measurement, really, there should be never a question that non-zero numbers like 5, 8, 3, non-zero numbers are always going to be significant. We would never write them if they weren't. But zeros are tricky, okay, especially since sometimes we make conversions, like especially in the metric system. Like if you measured something to be 25 centimeters, and you wrote it now as 250 millimeters. Is that zero significant? Well, no, that zero really wasn't significant because the initial number was 25. So you only had 2 digits. So numbers are never a question. Zeros are a question, okay? So there are 2 ways that zeros are significant, okay? Zeros that are in between significant figures must be significant. This zero would only be here if it mattered, okay? Otherwise, you would just put the 8 after the 5. Okay, so that zero's got to be significant. Okay, trailing zeros somewhere after a decimal place are significant. So this trailing zero is significant because, again, why would I even need to write it? What's the difference between 0.005083 and 0.005083? Mathematically, there is no difference. But by putting that zero, I'm saying I measured another digit. I'm trying to show that my measurement is a little bit more thorough, okay? So keep that in mind. Okay, now what about the cases where zeros are not significant? The leading zeros are never significant. So zeros at the start of the number, they're never significant, okay? They're placeholders. They're probably there because of a conversion issue. I always tell my students to think about it in terms of scientific notation. If you were to write this number in scientific notation, you would say 5 point blah, blah, blah. You would start with a 5. Those other zeros didn't matter. They were placeholders. They are not significant. So leading zeros are never significant. Now, what's not represented here is that trailing zeros are not significant if they are before the decimal. Okay, so let me show you what I mean by that. So, if we're talking about a number like 12,400, these are trailing zeros, but they're before the decimal place, right? The decimal place would be right over here. So these zeros are not significant. They aren't needed. If you're writing in scientific notation, you would not need to write them. Okay? So when in doubt, scientific notation is supposed to work with the idea of sig figs. Okay? So if you're not sure how to write it, put it in scientific notation and think about it. It might help. Okay? All right. So let me switch views here again. Okay. So let's talk about some examples here. So 125, all 3 digits are non-zero, so obviously they're all sig figs. 209.0. Okay, hold on. This is Miss Mac. I told you. You're going to hear from her a bit. Anyway, so 209.0, the 2 and the 9 have to be significant, which means this 0 is in between. It has to be significant. And this 0 is after the numbers. It's a trailing 0 after the decimal. It's significant. So all 4 are significant there. All right, 12,000 liters. Well, the 12 definitely is, but now these are trailing zeros, but they're before the decimal. That's not significant, so there's only 2 significant figures here. Then we have 0.000428 centigrams. The 428 definitely count, but what about these zeros? They're leading zeros. Leading zeros never count. 3 sig figs. Okay. And 0.041090. All right, so the 419 definitely counts, so the 0 in between definitely counts. This is a trailing 0, and it's after the decimal place. That doesn't count. This is a leading 0. Even though it's after the decimal, it's a leading 0. Doesn't count, so this has 5 sig figs. And 1140.0, this one throws kids off because they say, all right, the 114 is definitely is good. There's 3 digits. And this one, that's not in between sig figs, so why does it count? But it is between sig figs because this 0, like this one here, is a trailing 0 after the decimal, right? So that makes this significant. And that means that this now is between significant figures. If the 4 and the 0 are significant, then this 0 also is significant, so it has 5 sig figs. Now, there are different rules depending on whether you're doing addition and subtraction or multiplication and division. Most of what we do in here is multiplication and division, so this is the emphasis, but we'll talk a little bit about this at times, but don't sweat it too much. When you are doing multiplication and division of measurements, okay, you need to keep track of the number of sig figs. So for example, if I were multiplying 14.385 centimeters by 2.44 centimeters and figuring out the area of some piece of wood or whatever, okay, I would multiply them, but I have to keep track of the fact that this has 5 sig figs, this has 3 sig figs, and the rule is we always use the smaller amount or smallest amount of sig figs, okay? So that my answer is going to be limited to 3 sig figs. So even though when I multiply, I get this answer, 35.0994, I'm only allowed 3 digits, 3 sig figs. So I have the 35, and then I have to round off here to make it 35.1 square centimeters, okay? Now with addition and subtraction, it's a slightly different rule because it's not about how many sig figs, but it's about how many decimal places the numbers have. So in this case, I see I have 3 decimal places. This one I have 2 decimal places, and we go by the smaller number of decimal places for addition and subtraction. So my answer is going to be limited to 2 decimal places. So even though when I subtract, I get 11.945, I have to round off at the second decimal place, so it becomes 11.95 centimeters. Okay. Now notice, this had 3 sig figs. My answer had 4. That bothers people. Sorry. Okay, but that's the rules for addition and subtraction. Like I said, we don't do a lot with addition and subtraction. So if you are good with this, you should be pretty good with the idea of sig figs and math. Okay. Yeah. All right. Moving on. So the main thing is about dimensional analysis, okay? So hopefully you saw something like this in summer work, and different people set them up differently. We tend to call these our railroad tracks, okay? And I'll explain about starting amounts and equal amounts and all that. I usually get 2 things. Wait, 1, do I need to put units in my work? Well, that's the point of dimension analysis. And dimension analysis is a way of using the units to help you figure out what number goes where, okay? So I'll try and get into that. And couldn't I just do this by proportion? Well, this one you probably just do in your head. Yeah, there are some things you're going to be able to do just by, you could mathematically do by proportion. I'm going to tell you that once you get the handle of dimensional analysis, you're going to see it's a much better way, especially since proportion, if I have a 5-step thing, you've got to set up all these different proportions. I'm going to be able to do it all in one calculation, okay? And the more proportions you have, the more likely you are to make a mistake, without any question, okay? Teaching 32 years here, trust me on this. This is not my first time around, okay? So the key is figuring out the conversion factors, or what's labeled here as equal amount. Now you know that 1 foot is 12 inches. That is a conversion factor, okay? In the metric system, we can make up all kinds of conversion factors, like saying 100 centimeters is 1 meter, or 1 kilogram is 1,000 grams, and so on. Metric conversions, again, I do expect you to be able to know, okay? English conversions, even though I would expect you probably should know 1 foot is 12 inches, anything English related I'm going to give you, even if it's English to metric. So if you need to know that 1 inch is 2.54 centimeters, that would probably be given on an assessment. Homework, I know you can look things up. I'm not going to worry about that, okay? So the trick is just figuring out conversion factors. And, some conversion factors are basic things like, relating 1 mile, how a mile is defined as 5,280 feet, or a gallon is defined as 4 quarts, or interrelating metric and English units. 1 mile is 1,609 meters, okay? So those are, your basic straight up conversion factors. But then there's the inferred ones. Like if I tell you that the density of mercury is 13.6 grams per milliliter, what we're inferring is that 1 milliliter of mercury is equal to 13.6 grams. We're equating those. We're saying they're equal amounts for mercury. Okay? If a car is driving 55 miles per hour, I'm equating that 1 hour equals 55 minutes. If you're on a 2,000 calorie per day diet, we're equating 1 day with 2,000 calories. Okay, so we need to be able to pull those things in as well. And there's going to be more chemistry-related things as we get into the chemistry. Obviously, I'm just trying to pick some basic ideas here. Okay, so you'll see on this chart here, again, some of the same things that I've mentioned before. Okay, this is on one of the worksheets that I posted for you to practice. You see your metric stuff, and you'll see the English stuff. And in purple here, you have some English to metric conversions. Again, any of the stuff in red and purple, I would give you for an assessment. Anything's in blue, I would pretty much expect you to know. Now, as far as a year is 365.25 days, that's me being a technical science guy because of leap years and stuff like that. But technically, the decimal is different than just 0.25, but it's close enough. Let's move on. Okay. So, when you read questions, sometimes you got to figure out what kind of conversion factors are built into it. So let's read this question and talk about it. Gas cost $1.91 per gallon for me yesterday. My car averages 24 miles per gallon. My tank holds 61 liters of gas. If I am traveling from here to Orlando, a distance of 1109 miles, approximately how much should this trip cost me if the price of gas is constant? Okay. So we want to start by pulling out your conversion factors, okay? So again, reading here, $1.91 per gallon. That means that 1 gallon is $1.91. 24 miles per gallon means that 1 gallon is 24 miles, okay? My tank holds 61 liters of gas. 1 tank equals 61 liters. So once you've done that, then the question is, all right, so what is my starting value? Well, if this is a conversion factor, and this is a conversion factor, and this is a conversion factor, the only thing left is 1109. That's my starting value, okay? So now, let's go to the board and talk about that starting value real quick. And we'll talk about how we would set up the dimensional analysis. So, there. Okay. So we know that we have 1109 miles. Okay. So we set up the railroad path. Boom. If you like to put it over 1, that's fine. If you leave it blank, the 1 is assumed. Okay. So, in chemistry, 1s are usually not written. They're just left to be assumed. Okay. But it's okay if you put it in there. So now we're starting with miles. And we look at our conversion factors and say, what can I do with miles? Well, we were told that we get 24 miles to a gallon, so I can convert miles to gallons. Now, the thing about dimensional analysis is, well, am I multiplying, am I dividing? Well, you look at the units. Since miles are here, I know miles has to go here. You always go opposite. If the miles had been up down here, I would have put them up here. Okay, but wherever they are, you always go opposite. So if miles are here, then gallons is going up here. And we know that 1 gallon is 24 miles. We set it up like that because that allows us to cancel things out. So now that's canceled out. We no longer have miles. We have gallons. Okay? All right. So now what does gallons get me? Well, one of the other conversion factors said there was $1.91 per gallon. So we could say that there's $1.91 per gallon for 1 gallon. That allows us to get rid of the units gallon. So now I have dollars. Okay. What does dollars allow us to do? Well, dollars allows us to answer the question because the question is how much is it going to cost? I don't even have to use that other conversion factor that was given. Sometimes we do have extra information because there might be a part B to the question saying how many tanks of gas am I going to use or something like that. Point is, that's it. So now what do I do mathematically? I multiply the numbers on the top, 1109 times 1 times $1.91. I multiply the numbers on the bottom, 24 times 1. Okay, and then I divide. Okay, so I'm going to, let's try this real quick. 1109 times $1.91. So that's $2,118.19 over 24. Again, there's no units left down here. They all canceled out. The only unit left is $1. Okay, and now I divide that up just to simplify. So divide by 24, and I get something like $88.26. Okay, so that is the idea of dimensional analysis. Okay, by all means, ask me questions. We can meet in separate little groups or whatever else. But try, okay? Give the problems some effort. I have the problems up. I have the answers up. Give it a try. And let's try and get this done. All right? Talk to you soon.